Hello everyone, in this video we will be discussing about question 61 to question 70 of the ISRO Scientist and Engineer examination, which was held on 17 December 2017. Let's move on to the questions. That is the 61st question. Okay, in this question we have the match the following. There's a match the following, and we are talking about gang scheduling, rate monotonic scheduling, and fair share scheduling. So we would be discussing about what is gang scheduling. Okay, so gang scheduling is generally used by parallel systems. It is used by parallel systems. Okay, and in this it is related to scheduling the thread that are related to each other. That is, two threads, if they are related to each other, then these threads would be scheduled on two different processors. Okay, it is used in parallel system to schedule related threads on two different processors. So gang scheduling is related to thread scheduling. So A is related to T. So there is only one option in here, which is A. So our answer should be A only, but we would be discussing about other also. Rate monotonic scheduling, it is a priority assignment algorithm, and it is used in real-time systems. It is a priority assignment algorithm. So this is the answer, T and U. And fair share scheduling, and it would be guaranteed scheduling because it is the only one which is left. But what is fair share scheduling? That is it is used in those operating systems where CPU usage is equally distributed among users. Generally, the CPU usage is equally distributed among processors, but in fair share scheduling, the CPU usage is equally distributed among users. The same definition is for guaranteed scheduling, that is, the CPU usage is 1 by n times for n users. It is guaranteed scheduling. Okay, so fair share scheduling is guaranteed scheduling. The answer is A. Okay, so this is our 61st question. Let's move to the next question. Okay. In this, a system uses first in first out policy for page replacement, and it has 4 frames and no page is loaded to begin with. Such as we have 4 blank frames. The system first accesses 50 distinct pages in some order. Okay, in some order it is accessing 50 pages. Okay, and then access the same 50 pages in reverse order. Okay, so how many page faults will occur? Okay, we have 4, means the frame size is 4. Okay, the frame size is 4. So for accessing the 50 pages, there would be 50 page faults. When we would be accessing it in the reverse order, then the 4 pages would be there. So there would be 4 hit. Okay, and the remaining, that is 50 minus 4. The remaining 46 would have false. So 50 plus 46 false would be our answer, which is 96. So A is the answer. Okay, next. Which of the following is false? We have to tell which of the following is false, and here we are talking about 2 topics, that is user level threads and kernel level threads. So let's see what are user level threads and kernel level threads. We would discuss some difference between them. Okay, so user level thread is the thread which is implemented by users. Okay, kernel threads are implemented by operating systems. So you have to remember user thread by user, kernel by operating systems. Operating system does not recognize user level threads because they are implemented by users. Okay, so kernel threads are recognized by operating system because they are implemented by an OS only. And implementation of user thread is easy because it is created at the user level, and that of the kernel level is little bit complicated. Okay, so context switch time is less. Switching between the user level thread is less, whereas context switching in kernel level thread is more. So you have to remember these things. I think we have to remember this thing. Context switch requires no hardware support in user level threads, whereas in kernel level threads we need a hardware. If one user level thread perform blocking operation, then the entire process will be blocked. If there is a block operation on one user level thread, then all the process will be blocked. If one kernel level thread perform a blocking operation, then another thread can continue execution. See, the kernel level thread is, if you are working on a system, if you are working on a process and you are closing that process, another process would be in execution. This is example of kernel level thread. Let's move on to the question. User level threads are not scheduled by kernel. Okay, it is true because the user level threads, they are scheduled by the users. Okay, we can see the first option, they are implemented by the users and operating system does not recognize it. Okay, next, the context switching between user level thread is faster. Yes, it is true. Then the context switching between kernel level threads. Yes, it is true. Okay, when user level thread is blocked, all the thread of its processes are blocked. Yes, it is also true. Okay, so all these three options are true. So answer would be D. Kernel level threads cannot utilize multiprocessor system by splitting threads on the different processors or cores. Okay, let's move on to the next question. Which of the following is true with respect to deadlock prevention and deadlock avoidance schemes? So here we have two terms, deadlock prevention and deadlock avoidance. Let's see what are them. See, deadlock prevention, what is this? Deadlock can be prevented by preventing at least one of the four required. That is mutual exclusion, hold and wait, non-preemption and circular wait. If at least one of these conditions are prevented, then deadlock would be there. Deadlock can be prevented. Okay. Now what is deadlock avoidance? Deadlock avoidance is when a scheduler sees that the starting a process or guaranteeing resource to the process may lead to future deadlock. So this future deadlock states may be seen as the unsafe states. Then the processor is just not started or the request is not guaranteed. If there is a state which would be unsafe in the future, then the request is not guaranteed. The deadlock avoidance algorithm dynamically examines the resource allocation state to ensure that there can be never a circular wait condition, that there can be never an unsafe state. So whenever there is a safe state, it would give the resources, but when the state is unsafe, it won't. Resource allocation state is defined by the number of available and allocated resources and maximum demands of the process. So this is what deadlock avoidance is, and deadlock prevention, it is based on those conditions, the conditions which we are seen here, that is mutual exclusion, hold and wait, non-preemption and circular wait. Okay, now here in deadlock prevention, the request of resources is always guaranteed if the resulting state is safe. So in deadlock prevention, even if the state is safe, resulting state is safe, and those four conditions are not met, okay, then the resources won't be granted. So this is false. So our answer is the first one only, but we would be seeing other option also. In deadlock avoidance, the request of the resource is always granted if the resulting state is safe. Yes, it is always granted. True. Deadlock avoidance require knowledge of resource requirement a priori. Yes, there must be a knowledge of resources and the requirements of the resources. Okay, deadlock prevention is more restrictive than deadlock avoidance. Yes, it is true, because even if deadlock avoidance, only safe state is the condition, but in case of deadlock prevention, even if the state is safe, it won't allocate the resources if the conditions are not met. So answer would be A. Okay, this is our answer. Next, 65th question. Which one of the following are the essential features of object-oriented languages? Okay, the essential feature of object-oriented languages is abstraction, encapsulation, polymorphism, and inheritance. So these are the four essential features. And okay, abstraction, encapsulation, polymorphism, inheritance are the essential features of object-oriented programming language. The answer is A and D only. Next, which languages necessarily need heap allocation in the runtime environment? Okay. Heap is needed by the dynamic data structures such as tree, linked list. Okay, so those languages which allow the dynamic data structures are they required heap allocation in the runtime. So this is our option D. Okay, because global variables and dynamic scoping, these are not anyhow related to heap allocation. Okay, so dynamic data structures. Next. Okay, here we have a code. It is a C code, I guess, and in this we have to say that we have loop invariant. This is loop invariant computation or sub expression elimination, strength reduction, or code elimination, dead code elimination. So we have to see which of the following is false. Okay, in this we have to see which of the following is false. Okay, so let's start with the inner loop first. That is this inner loop, and in this condition. Okay, in this we have, see, here we have 4 cross j over here, 4 cross j over here. Okay, so same expression is in both the times, both way. So it is called sub expression elimination. This is a sub expression, and same expression is used both times, and the value of this expression is same within the loop. It won't change. So say within this, so it won't change within the scope. The value of expression is same. So this is true. That is, common sub expression elimination is true. Okay, next, see the next one. See this one, I mod 2. I mod 2. Okay, in I mod 2, so see the value of I would be same in this loop. In the inner loop, the value of I would same. So the I mod 2 will be same every time from 0, j is equal to 0 to j is less than n. Okay, similarly, the value of I is same in phi cross I also. So value of I would not change in the inner loop. It would be same. It is invariant within the loop. Okay, so due to this two terms, so it is loop invariant computation. Loop invariant. Okay, so our A is also true. Okay, now see, in place of this, suppose in place of phi cross I, in case of using phi cross I, we can use it is like x is equal to x plus is equal to, in place of this, we can use we can initialize this phi cross I with some value outside the loop only. Suppose here I have written p is equal to phi cross I, and here I should have written p. So the multiplication is converted into plus, only plus. Okay, so when the higher precedence operator converted into a lower precedent operator, this is known as strength reduction. Strength reduction. So here strength reduction is also there. So option C is also true. Okay, and from here there is no dead code, because we have n initialized to 0 for both. This loop would run n times, this would also run, and after completing this and this scope, this statement would also run. So there is no dead code elimination. So answer should be D. That is, the scope of dead code elimination, this code, it is not there. So this statement is false. So this is our answer. This statement is false. Okay, next. Okay, consider the following. Okay, we have to match this. Okay, each time a subroutine is called, its activation record is created. Okay, so activation record, whenever a subroutine is called, you can relate it like this. Whenever a subroutine is called, the activation related is created. So activation record is related to subroutine. So our answer can be either C or it can be either D. Next, what is the location? An assembler uses a location counter. Location counter, it is used by the assembler to give address to each instruction which is needed for relative addressing as well as for jumping labels. So location counter is related to assembler. So it is B is S. So again we have two options, that is either C or either D. And reference count, okay, it is used by garbage collector. Reference count is used by garbage collector to create the memory when the reference count becomes 0. That is, if in a location, if the reference count is 0, that is no one is referencing this memory location for a certain period of time, then it would delete, clear the memory. So reference count is used by garbage collector. So it is C. She should be the answer because R, S and Q is over here. But let's see other. Link loader. Link loader is a loader which can load several compiled codes and link them together into a single executable code. Thus need to be do the relocation of the object codes. So address relocation is linked to link loader. So it is D. So our D is P. That is D is connected to P. So answer is C, that is RSQP. Okay, next question. Consider this sequence with 100 cylinders. The request to access the cylinder occur in a certain order. In the following sequence, we have given a sequence, and cylinder is currently at 50. Okay, the head is currently at 50, and what is the time taken to satisfy is 20 milliseconds to move from one cylinder to the adjacent, and what we have taken is shortest seek time first. So what I'm going to do is, I would be writing it in increasing order so that it is beneficial for us. So our smallest is 2, then it is 4, then it is 7, then it is 6 and 7, then it is 10, then it is 15, then it is 19, then it is 20, I suppose, then it is 34, and then it is 75. Okay, it is 1, 2, 3, 4, 5 and 10. Okay, it is good. Okay, now the cylinder is at 50. It is at 50, they had it as 50. So difference between 50 and 75 is 25, whereas difference between 34 and 15 is 14. So shortest seek time is of 34. Okay, so we would come to 34 first, and the difference is 14. So I'll write 14. Okay, plus. We would be adding everything, 14 plus. And from 34, obviously 20 is nearer. So difference between 34 and 20 is, okay, it is 16. It should be 16. It is 50. No, it is 16. Okay, it is 16. Difference between 24 and 34 is, it is 14. Here the difference is 1. Here the difference is 4. Here the difference is 5. Then it is 3. Then it is 1. Then it is 2. Then it is 2. Okay, and from 2, then it would move to 75. Okay, it is 73. Then it would be moving to 73. From 2 to 73, it is 71. So we would be adding up all. 16 plus 14 plus 1 plus 4 plus 5 plus 3 plus 1 plus 2 plus 2 and plus 71. And it is equal to 119. Okay, so we have traversed 119 cylinders, and for traversing one cylinder you are having 2 milliseconds. So it would be into 2. It would be the time. So the answer is 238. Okay, 238 should be the answer. So it is over here. B is our answer. Okay, next question. A counting semaphore was initialized to 7. So initially its value is 7. Then 20 P operations and X V operations were completed. Okay, we have 20 P operations. So it is like P is wait. Okay, when P operations is performed, the value of semaphore is decremented by 1. And when V operations is performed, V is signal. When V operation is performed, the value of semaphore is incremented by 1. So initially it is 17. So we are performing 20 P operations. So we would be subtracting 20 P operations. Okay. After that, so our value would be minus 13. Okay. And after that, we would be performing what? X V operations. Okay. So X V operation is plus X. Okay. And the final value after these operations, the final value is 5. Okay, so that is minus 13 plus X is equal to 5. So X would be equal to 5 plus 13, and which would be equal to 18. So our answer is C. See, this is our answer. So this was all about this part. If you like the video, please click the like button. Please share the video, and please subscribe our channel. Thank you for watching.